Hello, welcome back, Honors Topics and Physics students. So we're starting a new chapter, and this chapter is on things that vibrate and waves and things like that. So there's some pretty cool things that we're going to be looking at this unit. So first off, every single atom in the every molecule of your body is constantly vibrating. So even when you're sitting still, you're in constant motion. And is there energy involved in a vibration? If so, what type? Okay, well, that's moving, so there's kinetic energy. There's some times when it's not moving, so where did that energy go if it was not in the form of kinetic energy? Probably potential energy. So vibrations and waves are ways of storing and moving energy around. And so it is definitely the story of energy. So normally I would do this with a physical object, but so picture this is a track and this is a little car, and these strings are actually springs. These lines are actually springs, and so we've got it attached on both ends to the ends of the track via springs. Okay, so if nothing is going on, if everything is just stationary, it's going to sit at what is known as the equilibrium position or the rest position. So that part in the middle is known as the equilibrium position. And what do we know about the net force on the car here? Well, if it's not moving or doing anything, we know that the net force has to be zero, or it's at equilibrium. Okay. If we set it in motion, it's going to oscillate or vibrate from one end to the other. The period is the time it takes to complete one oscillation. So the easiest way to do this is let's start a stopwatch when it reaches this left side. So we'll start and then let it go and then stop. Okay, so that's one complete oscillation. And that's known as the period. That's a term you need to know, and that's the time in seconds to complete one oscillation. Another term that you're going to need to know is what's called amplitude, and it's how far it goes away from the rest position or the equilibrium position. I don't know why I put home base there, but the very furthest extent it travels to the middle or the equilibrium position. Okay. So the amplitude is measured here by the center of the car, just to show you. So what type of energy does the car have? Well, we've already kind of covered that a little bit. So it's got kinetic energy when it's moving, and then at the ends, okay, when it's not moving, all that energy is in the form of potential energy. And the type of potential energy it'll have if there's a spring that's being stretched, okay, that would be elastic potential energy in this case. So a vibration is really just the transfer of energy between potential and kinetic. Okay, so when is the car moving the fastest? Okay, and these will probably be some multiple choice questions on the test, so you might want to make note. So it's moving fastest when it's at the equilibrium position. Okay, after that it starts to slow down. Okay. When is it stopped? Okay, at the very far end, when it's at the amplitude, when it's at its max amplitude. When is the car accelerating the most? Okay. Well, first off, does it have a lot of acceleration or little acceleration or zero acceleration at the equilibrium position? Remember what we said about the net force. Well, the net force is zero at the equilibrium position, which means that the acceleration is zero. So it stands to reason that it will actually have the most acceleration when its velocity is zero, which is at the very ends. Okay, so and that's because the springs are stretched the most, and so they're exerting the most force on the car at the ends. Okay, where's my? All right, so on to pendulums, which relate. And a pendulum is simply some sort of object that's on a string or a metal rod that's just allowed to oscillate back and forth like this, like a pendulum and a grandfather clock. Okay, And they swing back with a very, very even amount of time, which is why they're useful in clocks. So you can use this oscillation to measure time. Okay, the time it takes for one complete oscillation is known as the period, just as before. And the period is the time it takes to go from one end, okay, to the other end and all the way back. Okay, so that's important to know. It's not just from one end to the other end. That's just half of the oscillation. It's got to come all the way back. Okay. Now, some things you need to know about pendulums. Normally, we would have done a lab to figure some of this stuff out. But what do you think will happen to the period, the time it takes to oscillate? Is it going to oscillate back and forth more quickly, more slowly, or is it not going to change? Let's say I double the mass of the pendulum itself, so I increase the mass. What's going to happen to its rate of swinging? Okay. It ends up that it doesn't change. Okay. If we think about an object doesn't fall faster if it's compared to a lighter object. So heavy objects and light objects fall at the same rate. So the pendulum is not affected by the mass. Okay. What would happen if I double the string length? What would happen to the period? Okay, that would be the time it takes for one oscillation. Do you think it's going to take less time and be more quickly? Or do you think it's going to take more time and be more slowly, or not affected? Okay. Well, if you increase the length, it's actually going to the period is going to increase. It's going to oscillate back and forth more slowly. Okay. And we can think about it as having more rotational inertia because the mass is further away from the pivot point. Okay, that's one way of looking at it. Okay, what do you think would happen if we changed gravity? Let's say we brought our pendulum from Earth and we brought it to a planet that has more gravity. Do you think increasing the strength of gravity would affect it? Well, it ends up that it does. Okay, stronger gravity will cause the period to go down or cause it to oscillate more quickly, which is known as the frequency, by the way. We'll get to that term in a little bit. But how quickly something is oscillating is related to the frequency. Okay. So what about oscillating at a lower point? So releasing it at a larger angle. So how are we releasing it at a larger angle? So here I've released it so far, and here I've released it further. How will that affect the period? Okay. It ends up that the release angle, or how far you let it go from the equilibrium position, the bottom, doesn't affect the period. Okay, at least not very much. And that's something that's true in what's called simple harmonic motion. Okay, so which of these periods, these pendulums, has the greater amplitude? Okay, that would be the period at the bottom because it's swinging further away from the equilibrium position. Okay, the upper pendulum the lower pendulum has to travel a greater distance. Shouldn't it take longer? Okay, well, it does, but it's being released from a greater height, so it's traveling faster. So on average, that greater speed kind of knocks out the greater distance and ends up being the same deal. Okay, so as we mentioned before, pendulums. So here's the pendulum and this grandfather clock, which just swings back and forth, just a very, very small amplitude. What would happen to the period of the swing as the pendulum's swing height decreases? So let's say it's swinging at a very small amplitude, and let's say I increase that to a very large amplitude. What would happen to the pendulum, the period? Well, from what we just learned, it shouldn't really matter. Okay, what should happen to the period if I shorten this pendulum, and you can raise and lower this mass to affect how fast the clock is ticking? Let's say I raise the pendulum. What would happen to my period? Okay, it would decrease, so it would be swinging back and forth more quickly. Okay, this is the equation. You're going to want to make note of this for a pendulum. The period is equal to 2 pi times the square root of the length of the pendulum divided by the gravity of where that pendulum is located. Okay, so we see that if we increase the length, the period is increased. Okay, that's what the algebra says. And if we increase the gravity, we're going to decrease the period, and that's all what we've said. Notice that mass is not in our equation, and the release angle are not in our equation because they didn't affect the period of the pendulum. Okay, so a real basic problem here. A 2 kilogram mass on a 0.5 meter string is released. How long does it take to come back to your hand? Okay, so we see we're given the mass. Now we learned that mass does not affect pendulum, so we can just throw that out. We've got a 0.5 meter string, so that's the length of the pendulum. And how long does it take to come back to your hand? Okay, so that's to swing and come back, so it's asking for the period. So T is what we're looking for. I guess I should have made note that period is the symbol is T. We went through that fairly quickly. But at least we're covering it now. So plugging in, T equals 2 pi times the square root of 0.5 divided by 9.8. We use 9.8 because we're on Earth, or at least we assume we're on Earth. And we get that T is equal to 1.4. Okay, now that should be 1.4 what? Okay, period is time, so it should be seconds. All right, so a real basic problem. Kind of the flip side of that problem, how long of a pendulum would you need for a period of 1 minute? So this highlights a couple things. One is we want a period of 1 minute, but in order to plug that into this equation, it must be in seconds. So we got to convert that to 60 seconds. Okay, equals 2 pi times the square root of L, which is what we're looking for, divided by 9.8, just plugging in to the equation here. And I've done the algebra here. You should try this on your own, going from this to an answer, if you can do the algebra correctly. But if you do the algebra correctly, you get 894 meters. Okay. Now the period we mentioned is the time it takes to complete one cycle. Okay, so it's seconds per cycle, seconds per oscillation, that sort of thing. So really we just write down seconds, but it's really the seconds for one complete oscillation, or seconds per cycle. What is the frequency? Well, the frequency is how many cycles per second. Okay, so how do we get from seconds per cycle to cycles per second? We take the inverse. Okay, so frequency is equal to 1 over the period, and period is equal to 1 over the frequency. So that's also an equation you probably want to make note of. First Monday of the month, got the warning sirens going. Okay, so a pendulum swings back and forth in 0.25 seconds. What's its period and frequency? Well, it's back and forth in 0.25 seconds. Okay, so that's the period. So that's T. And to figure out the frequency, it's 1 over T. And that is, so that would be 4 cycles per second. And there is an abbreviation for that unit. It's called a hertz. And the symbol is Hz. You've probably seen hertz before, megahertz. I'm sure you've heard of that sort of thing. And that's where this comes from. So computers or the processor speed are rated in, I guess, gigahertz. Now, it used to be megahertz back when I was your age, but much faster now. Oh, here we go. So when we talk about frequency, it's cycles per second. Normally we leave off the seconds. Sometimes you'll see it as 1 over seconds, or seconds to the -1. But most frequently you're going to see frequency measured in hertz, or megahertz, or gigahertz, or kilohertz, or some sort of hertz. Okay? So which of these oscillations has the greater frequency? Okay, which is cycles per second, so oscillations per second. Okay. The one on the top has the greater frequency. It's occurring more frequently. It's got more cycles per second. Okay. And your radio dial, if you still even have one of these, So the radio stations are measured in megahertz or kilohertz. So FM stations, so if you listen to 93.3 FM, that broadcasts at 93.3 10 times 10 to the 6th or million megahertz, and AM is measured in kilohertz, 10 times kilohertz. Okay, so this simple harmonic motion is kind of what we've been introducing here. And basically, simple harmonic motion is an oscillation or vibration or something like that occurs where the amplitude does not affect the period. So basically, how big the swing is doesn't affect how long it takes for the swing. All right, and that's what we found out with the pendulum, was if we did have a bigger release angle, if we did have a bigger amplitude, it didn't make it take longer. Okay. So in true simple harmonic motion, the period is completely independent of the amplitude. So here we have a larger amplitude oscillation, and here we've got a smaller amplitude oscillation. They both have the same period. They both have the same frequency. All right. It ends up that a pendulum isn't exactly true simple harmonic motion, but it's pretty close. Okay. So an object on a spring, so let's say we've got a mass and we've got it hung from a spring, and we give it a plug, and we've got another one that's not oscillating quite as much. These do exhibit true simple harmonic motion, where the period, meaning the time it takes for an oscillation, isn't affected by the amplitude, which is how big the oscillation is. So here we've got a big amplitude oscillation, and here we've got a small amplitude oscillation, but they both take the same amount of time. Okay. Okay, so they both have the same period, but they've got different amplitudes. The mass on the left accelerates faster than the one on the right. Okay, why do you think it accelerates the mass more than the one on the right? Well, it's going to have that spring stretched more, and so therefore it's going to have a greater force accelerating it. Okay, so now let's again make sure we're keeping our vocabulary straight. So which of these oscillations has the greater period? The period is the time it takes for an oscillation to occur. Okay. This one has a much greater time for one oscillation. Okay, so this one has the greater period, but this one has the greater frequency. Okay, they're inverses of one another. Okay, which one of these has the greater amplitude? Okay, and remember, the amplitude is the bigness. Okay, the distance from the rest position, from the equilibrium position. Okay, and that would be the top one because it's a bigger oscillation. Okay, and which one has the greater period here? Trick question. It's the same. Okay. All right. So a little side note about an idea of what's called resonance. Remind me if I see you in class, I've got a demo I can do for this. This is little Jordan. Well, currently he's 14 years old now, but this was him when he was a youngin' in the swing, with a spoon, having a snack, I guess. So, and there, oh, here's Adrian. Didn't see him over here. Here's Adrian, my 16-year-old who just got a car and his driver's license, and so now he's feeling the independence. Something that if not already, you will know soon enough. So how do you get a big amplitude oscillation on a swing? Okay, you pump your legs, right? You got to pump your legs forwards and backwards and that sort of thing. Does the timing matter when you do this, or can you just pump them at any given time? Okay, the timing is critical. Okay, it's very important that you pump your legs at the right time. So when you're on a swing, you go back and forth at a certain natural frequency. That's in the case of being on a swing, you're like a pendulum, and that natural frequency is related to that equation that I gave you, 2 pi root L over G. But every object, like if you whack a ruler or I don't know, or hit a building, it'll oscillate with some natural frequency. If you continue to apply forces at the right frequency, you can make that amplitude of the oscillation get bigger and bigger and bigger. This idea is known as resonance. And what you end up with is a really big vibration, which on things like buildings and bridges, you do not want resonance to occur. Let's see if this video will go for, just lock up the computer. So here, and you may have done something similar to this. This is kind of like, moving back and forth on a swing. But here we've got people who have resonated this bridge. This doesn't look very safe. I'm not sure that this is a good idea, but they're jumping up and down at just the right frequency to make this bridge resonate. You've heard of sound resonating. What you get is a really large amplitude sound or a loud sound. So that's an example. Okay, so what I want you to do is work on the pendulum worksheet and watch your math show, work for the math, and good luck.